Hello everyone, I'm Jiaqi Gao, a fourth-year PhD student at Harvard University. Today I'm going to present Lyra, a cross-platform language and compiler for data plane programming on heterogeneous ASICs. This is a joint work during my internship at Alibaba with my colleagues from Tsinghua and Nanjing University. Recently, programmable devices have gained significant traction in the networking community because of their high performance and high flexibility. People have shown the tremendous benefits brought by the flexibility of programmable network devices. For example, consensus protocols, load balancing, network monitoring, storage, and congestion controls. All of the mainstream vendors are releasing their own programmable ASICs. Broadcom releases Trident 4 and Jericho 2 ASICs, and Cisco recently announced their Silicon One chip. Mellanox and Barefoot also have their own programmable ASICs. However, despite the bloom of the programmable network devices and languages, we found that the foundation of network programming on the data plane is still at an early stage. Network programmers are still using chip-specific languages and manually take care of the numerous details with hardware features, capacities, and network environments. This brings back to the era when programmers coding the software on CPU using the assembly language. We now use an example to show why current data plane programming is hard. This is the network sequencer, which is the critical component for maintaining the linearizability in the consensus protocols such as PAXes. Here shows the detail. The network sequencer injects the sequence header, a combination of switch ID and current timestamp, into the packet header on the selected flows based on their source IP. Well, for other packets, the switch drops them. The downswitch replica servers can then order these packets based on their timestamp. There are two major components, the filter table with two actions and the routing table. In general, there are three problems when programming the data plane. The first problem is the portability. The language these programmers use is low-level and chip-specific. Assume the switch that is implementing the sequencer is a Tofino switch, and the programmer is using the P414 language. Here shows the code to add the sequence header into the packet. What the programmer really wants to describe can be represented using the following two commands. The fundamental reason behind this is that P4 is a table-oriented programming language. It requires most of the logic to be implemented through the table, so it has a lot of overhead implementing such logic. Furthermore, different chip vendors may provide different APIs for their own specific ASIC. The programmer has to learn what are those APIs and sometimes even need to tune the program in a specific way so that the program can successfully compile. At last, different ASIC can support different data plane programming languages. For example, the Trident 4 switch supports NPL, while the Barefoot Tofino ASIC supports P4. In a nutshell, it is really hard to port one program written for one chip and migrate to another chip without modification. The second problem is the extensibility. Current programming languages focus on programming individual ASICs. They fall short when one program needs collaboration between multiple switches. For example, suppose we have two switches that can hold 1,000 entries respectively. The routing table of the switch requires 500 entries, and let's vary the filter table size. When the filter table requires 300 entries, we can easily fit both of the tables into one switch. But when the programmer wants to increase the number of entries to 800, the Tor switch does not have enough space to allocate. So the programmer has to put the filter table into the aggregation switch atop. But this brings a problem that the programmer has to rewrite the original program on the Tor switch and write a new program for the aggregation switch. When the number of entries again increases to 1,300, the table cannot fit into either of the switches, so the programmer has to split the table into two. One in the aggregation switch with 1,000 entries, and another one in the Tor switch with 300 entries. To make things worse, now the programmer needs to consider how to pass information between the two switches, because otherwise, the second filter table in the Tor switch does not know whether a first table is a hit or not, and will drop the packet by mistake. We can see that in these three cases, only the number of entries in the filter table is changed, but the operator needs to rewrite the program on the two switches and even consider how to pass information between them. The third problem is decomposition. When one program collocates with other programs, a practical deployment of a programmable data plane must have multiple programs enabled. For example, if the data center operator decides to add an ARP table with 300 entries to each Tor switch, and here is our smallest example with 300 entries filter table, we can see that after adding the 300 entries ARP table, the Tor switch cannot hold the filter table anymore. We need to rearrange the allocation. So we found that adding another program in one switch perhaps results in the rearrangement of the other programs on the same switch. We can see that any of the above three cases require a disproportionate amount of effort to program the data plane. And here summarizes the three problems. We believe the fundamental reason for the above three problems is lack of a high-level data plane programming language. Like we've said before, the low-level chip-specific language is the same as the assembly language that is specific to the architecture. Just like Dr. Brand said, the C language lets you get close to the machine without getting tied up in the machine. So we think now is the time to propose the high-level data plane language. So here we present Lyra, a high-level data plane language and compiler. Lyra offers a one big pipeline abstraction. It is the interface we provide to the programmer that hides the pre-mentioned three challenges. The programmer only needs to write down their intent through the Lyra language, and the Lyra compiler can solve those three challenges and compile the program into the chip-specific program for each switch. The compiler uses three key techniques to solve the above three challenges. First, Lyra builds one language synthesizer for each low-level data plane language so that the program can port between switches. Secondly, Lyra introduces topology-aware code allocation to deploy the program across multiple switches correctly. At last, Lyra uses chip-specific constraint encoding to make sure one or multiple programs can fit into the switch. Let's first see why we need a new abstraction. Traditionally, there are two models of network. The first model is a per-switch model, where the programmers program each switch individually. And as we introduced before, this model is too fine-grained and brings many challenges. On the other side, we have the one big switch model, which treats the whole network as a giant switch, and the switch is only in charge of delivering the packets between the servers. This, on the other side, is too coarse-grained that we cannot control where to allocate the programs, such as deploying an ARP table to all of the Tors. So we choose a one big pipeline model that provides a good balance and enough flexibility to the programmers, but not let them tied up to the detail of the topology. The one big pipeline model achieves the portability because it hides the switch chip information. Programmers no longer need to worry about deploying the code in multiple switches, and this solves the extensibility problem. In here, the programmer can simply assign the sequencer program should be deployed in these two switches. At last, the programmers can simply composite multiple programs together by overlapping the deploy scope of the pipeline. In this case, programmer can deploy an ARP table in each Tor switch. Now let's check how to write a Lyra program. So here is the sequencer's Lyra program. There are three sections. First, we need to define the header and parser. In the one big pipeline model, we only need to define one set of parser, because the package should be parsable for all the switches in the pipeline. Next is the pipeline section. In our example, since there is only one algorithm, the pipeline SEQ has only one element called sequencer. And the algorithm sequencer calls two functions, fSequence and the routing. The main logic of the sequencer is implemented in the fSequence function. In this function, we can see that the filter table is implemented by an external variable, and the size of the filter external variable defines the number of entries. Currently, there are 300 entries. So when the programmer wants to increase the number of entries, she only needs to change the size of the external variable, and Lyra takes care of everything else. Now, since the program is written, let's take a look at how Lyra compiles the program. The compiler has two components, front-end and back-end. We first check the front-end, which parses the input and run pre-processing and analyzing so that the backend can further process the program. Here is the Lyra program we wrote previously atop of the one big pipeline model. The front-end parses and processes the input Lyra program and returns the intermediate representation of the program to the backend. The front end expands the complex statements into multiple simple statements, replaces the branch conditions into a predicate, which indicates when the statements under the predicate are executed. And at last, the front end analyzes the dependency relationship of the statements. We can see that the fourth statement under the first predicate depends on the above two statements. Now let's check the backend. The backend has three major components: language synthesizer, chip-specific constraint encoder, and extensibility module. The language synthesizer compiles the Lyra into structured low-level languages. The chip-specific constraint encoder checks whether the program can fit into the switch. And finally, the extensibility module guarantees the program can correctly deploy in the scope. We will go through each component one by one. First is the language synthesizer. The reason we need multiple synthesizers is because different low-level languages have different programming paradigms. For example, we think P4 is a table-oriented programming language. All of the main logic is implemented by the tables. NPL, on the other hand, is a procedure-oriented programming language. In this talk, I will focus on the P4 language. As we just introduced, a P4 program is a composition of tables. Different packets may hit different tables in the program. Each P4 table has a match field and multiple actions. Different actions are executed based on the result of the match field and can never be executed at the same time. In each action, there can be one or multiple statements. And most ASICs require the statements in one action to be parallel, which means they have no dependencies between each other. Now I will show you how to compile a Lyra program into the P4 program. We introduce a data structure called predicate block. A predicate block is a group of statements that have the same predicate, but with no dependency. Here is a program we get after the front end, and let's see how to construct the predicate block. We check the first statement and create a new predicate block with predicate IPv4.srcip in filter. Next, we check the second statement and finds that it does not depend on the first statement, so it is merged to the first predicate block. So does the third statement. But as we said previously, the fourth statement depends on the second and third statement. In this case, we need to create a new predicate block. For the last statement, since the predicate is different, we also need to create a new predicate block. So after this step, we get three different predicate blocks. Next, we need to analyze the relationship between the predicate blocks. There are two types of relationships. The first is one predicate block depends on the other. This happens when one statement in the predicate block depends on one statement in another predicate block. So we can see that the second blue predicate block depends on the first one. The second type is mutual exclusive. This happens when the predicate of two predicate blocks can never happen at the same time. In our case, the red and the first blue predicate block are mutually exclusive. So now let's see how can we use the predicate block to generate the P4 program. As you can see, if two predicate blocks are mutually exclusive, we can merge them and build a table called filter. Given the input of the external variable lookup, we can decide the filter table matches on the source IP. Each predicate block can be converted into an action, and especially because action 1 uses the output of the external variable, the action has input parameter called server ID. And the second statement of action 1 is also rewritten. Similarly, we can convert the second blue predicate block into a new table called filter table 2. The filter table 2 has no matching field and only one action. And also because the two predicate blocks share the same predicate, the second table is only executed when the action 1 of the filter table 1 is executed. Till now, we get the synthesized P4 program. Now let's check the second step in the backend of the compiler, which is encoding chip-specific resources. This encoding process is similar to the chip-specific compiler that tries to allocate the input program into its ASIC. Take the RMT architecture as an example. The RMT switch requires if one table reads the variable written by another table, the first table should be deployed in the stage later than the second one. We can see on the left, we have the generated two tables, and thus we can introduce two variables as filter 1 and as filter 2 to indicate the stage each table is deployed in. We can encode the constraint that sFilter1 should be smaller than sFilter2 because filter table 2 depends on the filter table 1. We should also add a constraint that both variables should be deployed in one of the 32 stages. The SMT solver can quickly return the answer that sFilter1 equals to 0 and sFilter2 equals to 1, which means the two tables should be deployed in the first and second stage. We also encode other constraints, such as the SRAM TCAM memory, packet header vector, number of tables per stage, etc. Please check our paper for more detail. Finally, let's check how the Lyra compiler encodes the extensibility. And as we said previously, the extensibility module makes sure the program is correctly deployed in the downstream topology. Lyra needs to consider many rules to make this happen, and one of them is how to pass information between switches. In a nutshell, the upstream switches need to pack the data required by the downstream switches into the packet header. Again, let's check the running example with 1,300 entries. We know that in this case, the filter table is split across the two switches, and the downstream Tor switch needs the above table's hit or miss information. So the aggregation switch needs to add the table hit information into the packet header between the two switches so that the Tor switch can react to it. We also encoded other constraints, such as in any path of the scope, there's no code duplicated or missing or reordered. Okay, we've introduced all of the components in the Lyra compiler, and here is the overall framework. The programmer writes how to process the packet through the one big pipeline programming model. Next, the compiler synthesizes the low-level data plane languages through 3 core components and guarantees the program can fit into the switch and deploy across multiple switches. Now let's see how the system performs. First, I'm going to show a demo. On the left screen, we have the sequencer's Lyra program. On the right side is the configuration file, which defines the topology, the model of the switches, and where the pipeline ICQ is deployed. Remember, each switch can hold 1,000 entries, and the routing table uses 500 entries already. In our first case, the filter table has 300 entries. Now let's see how the Lyra program allocates the tables. We can see that Lyra compiler fits both tables into one switch, as expected. Next, let's change the number of entries in the filter table to 800. We can see that the compiler complains it cannot find an allocation strategy. So here we need to bring the aggregation switch into our scope. We can see that Lyra allocates 800 entries to the aggregation switch and successfully compiles. Next, let's continue increasing the number of entries to 1,300. This graph shows that Lyra program splits the filter table and put 1,300 entries in the aggregation and Tor switch, respectively. Now let's add another table, ARP table with 300 entries to the Lyra program. We also need to change the configuration file to add the ARP table into the Tor switch. As we said previously, the Tor switch cannot hold all of the tables, and thus the compiler moves the filter table up to the aggregation switch, which is also a valid allocation. Now let's get back to the presentation. We also wrote Lyra programs for other applications such as netcache, netchain, and even the switch.p4, and here is the result. We can see writing a Lyra program requires way less line of code than a P4 program. This is because Lyra uses a more compact language framework and the one big pipeline model. About the compilation time, we can see that Lyra can successfully compile the program for both languages in less than 2 seconds. And for the most complicated switch.p4 example, Lyra can still successfully compile in 33.6 seconds. Also, we can see that Lyra can reduce resource usage. In the netcache example, Lyra only uses 12 tables, while the original program used 96 tables. This is not the only example. We observe similar gains for other programs as well, such as netchain and speedlight. This is mostly because the manually written version kept many independent tables for modularity, but Lyra merges these independent tables into a single table. Here is the code for net cache. We can see that there are two tables with no matching field, and they are executed under the predicate that are mutually exclusive. Actually, in this case, we can merge the two tables into one table and two rules that match the nchdr.op field. We also evaluated the scalability of the compiler. Please check the paper for the result. In conclusion, Lyra is the first high-level data plane language and compiler that achieves portability, extensibility, and composition. Lyra offers a one-big pipeline programming model and can generate runnable chip-specific code across multiple switches. The programs generated by Lyra uses fewer hardware resources than human-written programs. That's all, and thanks for listening.